Of National Television News here at the Romulus, Michigan Engineering Center of Detroit Diesel Allison, where a press conference is being held to show the performance of its new electronically controlled engine system called DDEC. The conference is beginning with an overview of the DDEC system by Dave Marion, General Director of Engineering.
I'm really glad to be with you today and share an area of technological development that is going to have a dramatic impact on the trucking industry, the application of electronic fuel injection and engine controls. For the first time, heavy-duty electronics regulates engine governing functions, fuel metering, and injection timing. It will control idle speed, maximum speed, torque shaping, and provide programmable droop. The criteria for development was, of course, to maximize miles per gallon. This is largely accomplished by precise engine and vehicle road speed control while allowing us to meet the future stringent EPA emission standards set for diesel engines. I'm proud to tell you that we have approved for production the Detroit Diesel Electronic Control, commonly referred to as DDEC. Slated for availability on selected Series 92 engines in September 1985, DDEC will be the first totally integrated electronic fuel injection and engine control system available for heavy-duty engines. DDEC is a microprocessor-controlled electronic unit injector engine governing system. It generated from experimental studies in the 1970s where electronically controlled injection systems were constructed for use in combustion research. This work demonstrated the feasibility of electromechanically controlling the fuel injection process at the nozzles of a high-pressure fuel system. Adaptation of this control to the DDA unit injector system was undertaken in 1978 and has been under development since then. The DDEC system has been developed to Detroit Diesel Allison specifications as an integral part of our engines. Where possible, we have taken advantage of the design and manufacturing expertise in General Motors to provide the best and most cost-effective hardware.
Marion then told the press that after more than 5 million miles of customer testing in heavy-duty trucks and buses, the system is demonstrating fuel economy improvements of up to 10% over conventional mechanical injection units in the same fleet. DDEC also offers improved idle and PTO speed control, better cold startability, and a significant reduction in white or cold smoke. He said other benefits are integral diagnostic and engine protection features, and the elimination of many mechanical adjustments which will reduce operating costs. Next, Marion outlined DDEC's major components.
The heart of the system is an electronic control module, or ECM, that is mounted in the vehicle cab. The ECM's function is to compute fuel injection timing and quantity and transmit command signals via a wiring harness to the electronic distributor unit, EDU. The EDU functions as the high current switching unit that sends a signal to the solenoid-operated control valve in the electronic unit injectors, EUI. This controls the start and end of injection to regulate timing and fuel output. The electronic injector is similar in many respects to our mechanical injector in that the pumping, metering, and spray nozzle functions are combined into a single unit at the cylinder. Both injector designs utilize camshaft, rocker arm-driven plungers to generate the high injection pressures and employ needle valve nozzles. The EDU also monitors a solenoid voltage feedback signal, which is sent to the ECM for computing timing for the next injection event. Key inputs to the ECM required for engine operation are signals from timing and speed sensors and the throttle position sensor, shown as an electronic foot pedal assembly. Other sensors shown include turbocharger boost, oil temperature and pressure, and coolant level. These inputs are utilized in controlling acceleration fuel input optimizing engine starting, and providing diagnostics and engine protection. The flexibility of DDEC allows the same basic systems to be utilized on all DDA heavy-duty engines. Calibration data is stored in a programmable read-only memory chip called a PROM, located in the electronic control module. It allows us to customize the ECM for various ratings, adapt the system to 6 or 8 cylinder engines, and offer various application options.
Next came a demonstration of the system's operation.
Here with a 6V92 engine is Steve Weissman, Senior Project Engineer, who will demonstrate the engine governing features and rating flexibility. The first demonstration, the engine will be started with the oil temperature sensor placed in a beaker of cold oil, simulating a cold engine. The engine, go ahead and start the engine, Steve. You could see there maybe we could go back up to the beaker there with a temperature sensor in it. You can see we have the oil in a beaker with ice cubes around it, simulating the cold oil that you'd have during a start. If we now go down to the tach, you can see that we're at about 875 RPM, so we're on a fast idle for a cold start. Now we can take that sensor out of the cold beaker and put it into a beaker of hot oil, as indicated there with the beaker on the hot plate. You can see now as it senses that, the speed drops and we return to a hot engine idle of about 475 RPM. The next demonstration we'd like to do is a power takeoff demonstration. You can see on the screen that we have a PTO control, such as what you'd have for a utility vehicle or a bulk unloader. And what Steve will do now is to increase the speed through the remote control that you'd have in a vehicle, take that up to 1500 RPM, where you would set that for control of your whatever you're going to be driving from the PTO. You can see that we have a minimum torque, again, on the engine. What we'll do now is to increase the torque up to about 230, equivalent about 230 horsepower, and show you how precisely that engine speed stays at 1500. You just see a little quivering of the needle on the RPM. You can see now we're up to about 820 foot-pounds of torque, which is equivalent to about 230 horsepower on this particular engine. So that quickly we stabilize both speed and load. Now we'll dump the load off. You see the needle just take a slight movement. But then as the sensors pick up, we bring us right back on precise speed control.
Next, Dave, Marion, and Steve demonstrated the total control DDEC has over the operating characteristics of the engine. First, they ran an engine rated at 300 horsepower at 1800 RPM with 125 RPM droop. Then they switched to another electronic control module to show that the same engine could be made to produce 270 horsepower at 1750 RPM and operated zero droop. This allows Detroit Diesel Allison to customize the performance characteristics of the engine to meet very specific operating conditions when the vehicle goes into service, and even change them later.
Now let me give you some specific data on fuel economy results from our field testing. We have had some customers report 21% improvement in fuel economy. However, the data presented here shows that in 4 different fleets with over 400,000 miles of testing, we have achieved up to 10% improvement.
The trade press editors are now moving out to a large tent behind the engineering center, where they'll be given a demonstration of DDEC's performance by Detroit Diesel Allison on-highway marketing manager, Al Kozel. His demonstration concentrated on the engine protection system, the ability of the components to function in the day-to-day environment of a highway tractor, and the built-in diagnostics. Kozel used a display panel and DDA technicians to assist with the visuals as he demonstrated high oil temperature, low oil pressure, and loss of coolant. Here he describes high oil temperature.
Now remember that the hot oil temperature could come about for several reasons. We could be low on oil, so we've got less oil absorbing the heat. We could have a maintenance problem, so we've got a plugged oil cooler. And we could be driving under very high ambient conditions. For instance, we're driving through Death Valley. In this case, we might want to say we're doing all three conditions at the same time. Let me show you what will happen. Normal conditions, we've got the engine at 1500 RPM and we're driving along, and this is 229 degrees. Now I'm going to switch the sensors from this beaker to this one, which simulates 252 degrees, hot oil but not totally critical to the life of the engine. Listen for the engine sound and watch these panels. Now it started to bring it down in power slightly as the check engine light went on. And to show you that that's all that caused it, I'm going to put it back on regular, and as soon as the sensor picks that up, it's going to increase the power back up. So we're going along with this hot condition, and the check engine light comes on, but the operator in this case continues to drive. He does not take heed of it, and our condition, whatever is causing it, continues to worsen. The oil cooler is completely plugged, and we go to hot oil. And immediately, the engine starts to sense it, the stop engine light comes on, and the engine now starts to reduce itself slowly in power. So we're putting less heat into the system. He's got some time to get off to the side of the road. He understands what's happening because this would have been explained to him as a DDEC driver. And you can see the RPM coming down. Remember, this would be actual horsepower coming down. We'll come down to 500 RPM, and the engine will shut itself off.
Next, Kozel showed how DDEC functions in a low oil pressure situation. They restarted the truck and pumped oil out.
At about 23 pounds, both lights will come on. He now knows he has a problem. He has an option that I won't share with you yet, but the RPM and the horsepower start to come down. He's got a little bit of time to get off to the side of the road or out of traffic or whatever is necessary. Interesting thing is that the temperature did not go up in this case, so he would have no sense of that. The oil pressure would be the only thing, and if he wasn't totally watching that, DDEC again would have stepped in and prevented serious damage to the engine. All right, now we'll pump the coolant out. And in the case of the coolant, he does have a temperature gauge for coolant, but this really isn't going to help him because there's not enough time for that coolant to heat up and the gauge to react to give him the signal that, in fact, as we were going down the left lane of the I-94 through Detroit, the hose just went. So we're starting to dump coolant. Now the check engine light and stop engine light came on. That's his first signal that he's losing coolant out of the back of the bus, and he's losing power, but he's in a left-hand lane, and we want to give him enough time to get over off to the right side because there's a concrete barrier. He doesn't want to bust there. So next to these lights, he's got an override that's good for 30 seconds of additional power. Jeff? It brings him back up to the reduced power level, and in fact, after he let it off, he could hit it a couple more times, but he cannot continuously hold it and continue to run at that reduced power, but this is a way to give him a little bit of extra time to get into a safe position with the vehicle.
How does DDEC function if voltage is low? This was shown by disconnecting the alternator and deliberately discharging the batteries. The truck was started with an auxiliary battery. With low voltage, the operator would sense difficulty with the normal electronics, but DDEC would continue to operate the engine. Here, the voltage continues to drop.
We're down to 8 volts. Turn signals aren't working at all now. And he would be driving under full power to get the vehicle home with no alternator. What happened is now DDEC just went into a built-in backup system. This system would go into effect if there is reduced voltage, or for instance, if somebody chose to actually remove the entire PROM out of the ECM unit, it'll still go into backup and run off of a backup built-in computer. Now you lose some functions when you do this, but you do not lose the ability to drive the vehicle. For instance, we'll lose all smoke control over the engine. We'd have no cruise control, we'd have no road speed control. We'd have no of the automatic engine shutdown systems. If this engine was rated for 2100 RPM, it would go to 1800 RPM, and then from that point, it would drop down another 10% in horsepower. So you'd have that ability still to move the vehicle, and the DDEC would have more the ability to continue functioning while other things did not. Now, if you think about how long can he operate it, if this truck had only one battery, fully charged, at night we could drive this truck with all the accessories on for an hour and a half with a DDEC. With one fully charged battery in the daytime, we can operate for 4.5 hours. So we've got more than sufficient time to get to a service facility or at least into a safe position with the vehicle. So low voltage power down to that kind of a level where there are other electrical failures on the truck still will not adversely affect DDEC's operation, because we've kind of tried to think about that as we've gone through the system, recognizing that that will take place at some point in time.
The EDU, electronic distribution unit under the hood, was sprayed with high-pressure water to show its durability.
The connectors to this system are weather pack connectors designed to live under the environment of the hood. And this is really a little more abuse than they should be taking, but we're going to subject them to it anyway. This has worked every day so far in practice. I'm sure it's going to work again. Okay, Larry, put it right on the connectors and the sensors. And we're doing this with the engine running to show you that if there was a problem, it would shut itself off. It's going to keep running. Now, the other major component of the unit is located within the cab itself. And this also has to be impervious to some operating conditions, not exactly what we showed there. I mean, this isn't going to get water pouring on it or anything like that. But there is dirt. There might be salt residue in the wintertime or sand, and the fan blows it around inside the unit. And if you put your hand under the dash panel of a truck after a couple of years, there's dirt. And somebody also might decide to pour water, or a cup of coffee spills on the dash panel, goes down through the defroster system. So there is some abuse that has to be built into this. And I didn't want to take the time to subject this thing to 2 years of dust, so we buried it. And this is the ECM out of this unit. We're pretty confident there is not a problem with dust getting in here, certainly under normal operating conditions and even under this abuse. Now, this is sort of a dirty mess, so I'm going to wash it. And again, this is not the recommended procedure, and if we can ask our fish to move out of the way. We're going to totally submerge that, and for purposes of demonstration, this is just to show you that, in fact, this plus all of its connectors are also waterproof. Even this, and don't laugh, it's not nice. It could happen to you someday. Well, we're having a little fun. Dave mentioned something to you, and I don't know if you caught it all, but he said there was a built-in idle clock. That's what we just did. When Al actuated the air brake, we actuated a 3-minute idle clock. The actual ones that will be in production are 5 minutes. For seconds of time here, we decided to pick 3 minutes. And that's what we did, because this is really fuel savings. That's not an ECM in the water. That's an ECM saving fuel. Drive past every truck stop and try to figure out how many gallons of fuel are being wasted because the engine is running. So automatically, after 5 minutes with the parking brake on and the engine running, it's going to shut itself off. And that's untold fuel savings. That does not have anything to do with all the tests we run. This is over and above. Now, if that story all holds true, this ought to start again, right? Give it a shot. I got guts. All right. It really does work.
To address the serviceability of DDEC, a simple, inexpensive diagnostic tool has been created.
This is the investment we're going to ask the dealer to make. This is the whole thing. All $395 of it. I'm going to demonstrate to you what it does, because we want to be sure that the service is stepped up to on this engine easily without making it complicated, and that in fact every service technician and every service dealership has the ability to use the advantages that are built in of the diagnostics out of DDEC. So this is the system, and later on we can pass this around and let you look at it. On your card now there are two sides. One side of that card shows the diagnostic codes, and the other side an explanation of the abbreviations. The abbreviations refer to the settings on the top of here, we can, all the various things we can do, and the codes then are simply, it'll come up with a number and it'll tell you what happened. We've demonstrated some failures here. So if the system works, we ought to find out what those failures are. Al, please. The failure we demonstrated here are really two. We had low voltage, and because we went into the backup system, each of the injectors had an interruption and a reduction in power. So if the system works, through this digital data link, we ought to be able to read that. And here are our codes as to what's taking place. These are the signals, the 3-digit signals, and if you look at your card, you'll see a 31X, and those are the signals that an injector had a problem. In this case, we know what the problem is. The unit would come into a dealership. He would clear all the codes after he heard the complaint, turn this on. In this case, the injectors would not flash because it would be up to full power, but he'd know what the problem was, and the fact that it was reduced voltage, which shows up on here, would tell him what had taken place.
To show more diagnostic capability, an IBM PC was connected to the other unit.
First thing we get is we get a fingerprint on the engine as to what it is. This is a 1985 8V92 jacket water after-cooled engine, 475 horsepower at 2100 RPM, programmed with 150 RPM of droop in it. It's not running, so the engine speed is 0. This tells us the pulse width, the amount of fuel that would go into the engine. Temperature, turbo boost, throttle, beginning of injection, oil pressure 0, coolant level is full. And it also tells us there have been some codes logged here. And we're going to ask Greg to bring those codes up. And the first thing we're going to see are the malfunction codes, and they're exactly the same 3 that we saw in the digital readout. And they're spelled out: low coolant level, engine oil over temperature, and engine oil pressure is low. Now we're going to take this in one step farther and show you what happens if, in fact, let's say it's a low power complaint and it's caused because there's some dirt in the fuel system. We got a plugged injector tip, so the driver comes in and says, I got low power. And that's a kind of normal thing that takes place. Watch how quickly we can tell you which injector, in fact, is doing that. We've deliberately programmed this to do it. This is the normal amount of fuel it should take in an injector in this operation. And now we're going to cut out individual cylinders, and we're going to be able to see how much additional fuel is required to be picked up by the other cylinders in order to make up when we cut this one out. That's the yellow block, is the additional fuel being used by the other injectors. Now when number 3 came up, it showed that we maintained the same power even though it was out, and it did not take additional fuel in the other injectors. That says to us that's the injector that in fact is plugged now. Okay, Rick? That's how quickly we were able to find out which cylinder had the problem. Think about the mechanical way of doing it. Driver comes in, says, I got a low power complaint. We lift up the hood, we take off some plumbing, we take off a rocker cover, we take a screwdriver, and we short out the 4 injectors. I don't know how your luck goes. Mine is it'd be on the other bank. I know it would be on the other bank no matter where I start. I think it moves. Probably be the last cylinder that I get to. That would take an hour on this engine. We did it in about a minute and a half, and we did it with accuracy. There's no guesswork. We now know exactly which cylinder it is. And within the DDEC system is a lot of this kind, and we wanted to demonstrate just that one thing for you. Now, we said we had some fuel economy tests going on. And first, let me tell you about the trucks, and Dave told you a little about them. But the first pair of trucks you're going to see pull up are a pair of Astros from H.O. Wolding of Nelsonville, Wisconsin. And they're driven by 2 Wolding drivers that have been working with us for the last couple of weeks, John Popp and Cliff Patoka. They're 2 practically brand new trucks, 6V92 air-to-air engines, except that we retrofitted one of them with DDEC. Now these trucks were run on the route that Dave described from Milford to Grayling and back, about 2,230 miles. First of all, the Wolding mechanical unit went 2,227 miles, 364.5 gallons of fuel. I'll calculate it for you, that's an average of 6.11 miles per gallon. The Wolding DDEC unit went 2,234 miles, used 332.15 gallons of fuel, 6.73 miles per gallon. That's an improvement, and if somebody guessed this right on the mark, you get the win. 10.15% better. Other trucks that we've just pulled up here next to the Woldings are the pair of roadways that Dave described. 1984s, driven by Ralph Dunnigan and Wally Qualis. And these had more miles on them when we converted them. There was 197,000 miles on one unit when we got it and 139 on the other. They're 6 V92 jacket water engines. Let me give you some numbers on those. The roadway mechanical unit during this test went 1,277.3 miles. It used 234 gallons of fuel. Pulling doubles, that's 5.46 miles per gallon. Now the roadway DDEC unit went 1,269.2 miles, used 209.9 gallons of fuel. That's 6.05 miles per gallon, pulling doubles. That's an improvement of 10.81%. Think about that, 10% because of the addition of the electronics. And if one of these trucks was to put on 120,000 miles a year and the base engine was 6 miles to gallon and they were buying fuel for $1 a gallon, they just saved $2,000 in the first year. I will tell you that's more than the OEMs have quoted anybody so far for the price of DDEC by a substantial amount. So fuel alone would have well paid for it in well less than a year. All the benefits of the engines we just saved here are in addition to that. The time and obviously the expense that goes along and the downtime that's saved with the diagnostics just all adds up on top of that.
Members of the trade press have had a full day watching this amazing new electronic engine system show its flexibility and reliability. Then driving and riding in DDEC-controlled trucks and looking at high-tech displays. Chief Engineer Dave Marion told the group, and I quote, "Someday a mechanic in West Bygauche, Nebraska, who runs up against an engine problem he can't solve, will be able to hook his computer to the phone and transmit data to an engineer in Detroit who can diagnose the problem without leaving his desk," end quote. DDEC is here, and Detroit Diesel Allison has it. I'm Jerry Whitman reporting for National Television News from the Detroit Diesel Allison Engineering Center in Romulus, Michigan.